Suppose you test positive for some virus. What's the probability that you have that virus? Now, you might think, well, I tested positive, I must have the virus, right? Not so fast. For one, testing protocols are not perfect. Some tests have false positives where they say you're positive and you're not. They can also give false negatives where they say you don't have it, but you do. And this is, in fact, the case in the real world with most tests. Also, what may happen is that the virus is not very prevalent in the population. So the question is, if you, let's say one of you tested positive for Ebola or anthrax or some really, or the bubonic plague or something. These are all really rare in the population. If you if you randomly went to the doctor, not because you were feeling sick, but just randomly went and tested yourself and tested positive, do you think you would actually have it? So let's see. Let's see what happens. And I went and researched some actual numbers for COVID tests because when I originally wrote this problem, it was all about COVID and COVID PCR tests. So let me give you the numbers that I found and some terminology. The question that we're going to address is, given a positive COVID test, what's the probability of actually having COVID? And notationally, how about I define capital T to be the event that a randomly tested Ada County resident tests positive, and capital V, the event that a random Ada County resident actually has COVID. And here's some related terminology. In the context of medical testing, the sensitivity of a test is the same as the true positive rate of the test. In other words, it's the probability that someone that has the virus tests positive for the virus. The specificity of a test is the true negative rate of the test. That's the probability that someone who does not have the virus tests negative for the virus, okay? Finally, the prevalence of a virus in a population is simply the proportion of the population that has the virus. So if we're choosing citizens at random, this is simply the probability that our random citizen has the virus. In other words, P of V. So what we want to find is the probability that someone who tests positive actually is positive, P of V given T. And I went and looked up the sensitivity, specificity, and prevalence, at least when I wrote this problem. So when I wrote this problem, they were using these PCR tests that had that according to some website that I found, had a sensitivity of 80% and a specificity of 99%. So 0.8 is our true positive rate. 0.99 is our true negative rate. Finally, I went and looked up how many cases were in Ada County, and I found that at the time I was writing this problem, there were less than 10 cases per 100,000. So let's just assume a worst case scenario that the prevalence is actually equal to 10 cases per 100,000 residents. Okay, so we'll assume a prevalence of 10 over 100,000 or 0.0001. Okay, that was quite the setup. We're now ready to solve the problem. And you have some similar problems, by the way, on the online and written homework. What do we want? We want P of V given T. Now, you don't obviously know what P of V given T is, but we do have these three quantities, which are all conditioned on V, not conditioned on T. So we have to reverse our conditioning, which is what Bayes' rule allows us to do. So let's apply Bayes' rule. All right. So P of V given T is, according to Bayes' rule, it'll be P of T given V, P of V, over, then the first term of the denominator is always the same as the numerator, then plus, does anyone remember what the second term is? Where does the prime go? On the T or on the V? On the V, good. T given V prime, P of V prime. And let's see what we know and what we can figure out. So we know that 0.8 is P of T given V. So we know this term, which is the same as this term. We have a prevalence, P of V. So we know this term and this term. Okay. I still need a couple more terms though. What do I do with P of, how do I get P of T given V prime and P of V prime? Oh, good. P of V prime, we can use the complement formula to get that it's 1 minus P of V. So that's 1 minus 0.0001 or 0.9999. Okay, I'm making progress. This term is this one. There's one more term to figure out, and that's P of T given V prime. Pay close attention because this is the hardest part of this whole problem. And you're going to run into something similar on the homework. Pay very close attention. How do I get P of T given V prime? I don't know what it is. I'm not given it. What I am given is the true negative rate. How does that help though? Because right, we haven't used this 0.99 number yet. What's the relationship between P of T given V prime? I guess that would be the probability that you're negative but test positive. So that's a false positive. What's the relation between the false positive and the true negative rate? Oh, yeah, we can apply the conditional complement formula. This is 1 minus the probability of T prime given V prime. So it's 1 minus the true negative rate. 1 minus 0.99 or 0.01. Fantastic. We have everything that we need to use Bayes' rule. You're going to do something similar on the homework, by the way. I wrote a written homework problem where this is like, this is like a variable. Say like, whatever this thing is, if you call it X, then you'll need a like a 1 minus X expression in the problem, which you probably haven't seen yet, but that's the trick that you have to make in order to solve the problem. So we took 1 minus the true negative rate to get the false positive rate. Thus, okay, so this is equal to, let's just plug in all our numbers. It was what? 0.8 times 0.0001 over 0.8 times 0.0001 plus 0.01 times 0.9999. And this comes out to be about 0.00794. So less than 1%. So how about that? You test positive, you think you have the virus, not so fast. There's a less than a 1% chance that you actually have the virus. And this is largely a consequence of the low prevalence, by the way. Like if it turns out that, I don't know, like half the population or a large portion has the virus, then the probability of a false positive becomes much decreased, becomes much less. It's only because the virus is so rare that this is the case. Also, this assumes that residents are tested randomly. In practice, this may not be the case. In practice, you're probably not even going to get yourself tested unless you feel sick or otherwise have some reason to think you need to be tested. So this neglects that bias towards people that are sick. It assumes that a resident of the county was randomly chosen to be tested, with all residents equally likely. Cool. So that's the medical test paradox.